Okay, so today we're going to talk about the fast Fourier transforms, and I'm going to do a very specific application. Okay, and the idea is to kind of highlight some of the big level ideas of what the FFT can partly be used for. The idea of thinking about time and frequency when you think about signals, and give you some of the first ideas about how to do very basic signal processing. Now, start off with the following. What do you think? Legal statements that you can't tie me to this or hold me down to this. So this is a very simplified version of signal detection and signal analysis. So a radar is actually more complicated than what we have here, but the basic ideas are all here. And then you just do something fancier, and we'll talk about what the fancier part means as we go along. Okay, so here's the basic idea. This land is your land. This land is my land. And up on here, we're going to put a radar. Yeah, exactly. There's my little antenna dish. Okay? Now, if you remember growing up, well, in my generation growing up, we always used to see the TV shows. And whenever you'd have sort of some kind of science show, there'd always be a cutaway shot to a radar going around. And like the $6 Million Man, there'd always be something then going to a radar shot. Back then, we used to chloroform everybody on TV. Back then, all the bad guys, there was no violence. You just chloroform them. You just put a little white thing, and they just faint. Remember this? You guys didn't get this. You guys don't even probably know what chloroform is because you were devoid of chloroform on TV. Chloroform was in every show growing up. Okay, so there you go, chloroform and radars. This is back in the day, and this is your radar. And here is yeah, that's right, jet airplane flying along. Let's put some flames here just to really give it some special effects. Okay, so here's the deal. I have a plane perhaps coming into my land and your land over here, and we want to detect this plane. Now, typically, jet airliners, we know where they are. They tell us, by the way, I'm flying in your friendly skies. Here's your captain. We're right over Michigan. Everybody knows where they are. They try not to hide. Okay? In fact, they want to be very visible so that nobody else runs into them. However, maybe this is a plane, and you want to detect this, and it's a fighter jet. And so here's the idea of the radar. What you're going to do is send out, typically, microwaves, radio waves, out into space with, let's say, some frequency omega naught. Okay? And the idea is you just send it out there to space, and when it hits an object, it bounces off. So this is all omega naught bouncing off this airplane. Your objective is you're sitting over here on this dish, whatever gets bounced off back towards here gets picked up by a small portion of what you sent off gets picked up over here. Okay, so you send off a pretty strong signal in hopes of getting a small return of this omega naught. And if something came back, then you know bounced off something. Okay? Now typically you know that maybe there's a mountain over here, maybe there's a lake here, it's very beautiful, some nice trees. Put the trees where you like them. Do you remember that? We grew up on that too, the guy who does the art on MTV. No? Okay, some of you know that reference. This is a cultural learning class, and clearly you guys need it. All right. So the idea is you have all this stuff that's going to give off the standard signature. So you can kind of in some sense say, I can subtract that out. And what I'm looking for is in addition to this, do I get anything else back? Okay? So that is the idea of the radar. Now here's the problem. So for instance, over here on this land camping is Erica. Okay, and she's camping with Maria. And they're in the great outdoors, but they got cell phones still. And they're talking, calling their mom in New Jersey. They're polluting this whole airspace. So it's just not omega naught that's floating around here. It's all kinds of stuff. There's a little AT&T tower over here for its 3G network that's gotten all kinds of heat. there's stuff everywhere. You pop lots of signal everywhere. So when you detect stuff, it's not like it's this pristine environment. You're picking up full range of electromagnetic spectrum. Okay? And all you want to do is figure out, I'm bouncing off something, and I want to detect this thing. So I want enough signal to do this. Okay? But within all the stuff that I read in is this whole array of electromagnetic energy. And I've got to figure out how to take care of that. All right? Now, that's your perspective sitting over here. Now, let's talk about the perspective of you being up here in this airplane. And you want to go undetected. So, what are your options? Well, one option is just to not fly in this space. That's option one, stay home. But suppose, okay, you don't have that options. You've got to go flying here. So what do? Well, what if I built this plane out of materials that absorb omega naught? Crazy idea. Not really, right? This stealth technology. The whole idea is you put this special material on, so when omega naught hits it, it just gets absorbed instead of rebounding. The whole premise is that this thing here relies on the reflection. If there is no reflection, there's no detection. Okay, so you try to absorb as much as omega naught as possible. Okay, that's one. Two, how do I build a plane that has very few reflections to begin with? For instance, I can design the plane where all the edges are very smooth so that, for instance, I minimize even the amount of reflections off just the geometric surfaces. Okay, again, if you look at these stealth planes, they are just these, like the B bomber wing plane. It's smooth, no corners. They even put the missiles hidden underneath so that there's no reflections off things. Reflections are detections. Do you see that, how it rhymed? I just made that up right then, but I should have been a poet. All right? So there you go. That's one option, is you build the geometry of that plane, and that's a pretty big industry. Right? I want to come in here, and I don't want anybody to see me, so I can try to figure out how to stop those reflections from coming back. Or, you're not going to stop all of it, but what you want to do is reduce it to such a level that this guy over here thinks perhaps that you're just a Canadian goose flying in the sky. Maybe you're a pack of geese. Okay? That's what you want this person over here to believe you are. You may be armed to the teeth, missiles, and you're like a 40-foot-long jet flying in at Mach 5, but you want this guy to think, oh, there's a Canadian goose moving at Mach 5. Okay, all right. We'll talk about picking up speed and so forth in a little bit. So that's what your objective is. Now, another way to handle this is to, fly one of these AWACS planes way up high in the sky. Have you seen these ones? Now, I'm going to talk here, be gender specific for a moment. If you were a boy, potentially you had a book about jet airplanes when you were a kid, and you flipped through that thing, and that was like the coolest thing ever. So it's about 7 or 8 years old. Maybe you did that as a girl too, but I know for a fact we were boys. And there was this airplane, which we always thought was dorky because it didn't look like it could move very fast. It had that little thing on top. What's the whole purpose of that thing on top? In many ways is, again, big picture. It's like, yeah, this guy's trying to read omega naught so he can pick up this stuff here. Why don't I just fly really high, and I'm just going to blast out omega naught everywhere, right? Flood the whole space. So this guy's going to pick up a ton of omega naught, but he's not going to see this one. By basically inundating all the space with all the signal, I can basically fly something at a very small thing through because they go, I flooded the system with omega naught. Is that understandable? It's kind of like a radar jamming issue, right? Now, it's like, yeah, this thing's up, but this thing's 30,000 feet up in the air. This thing here is 200 feet up in the air with missiles. This thing here, I'm not going to launch a missile at it, right? I mean, ultimately, the other part of the story is, with this land is your land and my land, right over here sits, these are missiles. Pretty nice rendition, you think? And you're going to make a detection, and you're going to have to also make a decision about, hey, should I take one of these and put it over there? Now, if you think it's a Canadian goose, you totally do it. Because if you've walked by the pond, you hate Canadian geese, right? You walk by there, and you step in stuff, and they're mean. Has any of them hissed at you? Who's gotten a goose hissed at the UW before? Okay. So for those of you who are first years, please walk a little closer to them. You'll get the hiss. You'll get the whole experience here at the UW. There you go. Okay. So you would, after that experience, decide, yes, it's a Canadian goose. Launch a missile. Okay. And hopefully there's like 3 or 4 of them. So you can just clean them out all at once. Okay. So that's the radar problem. We're trying to make a decision, ultimately based on, let's say, a low signal to noise ratio. Okay? They're trying to go undetected. You're trying to pull that out. By the way, this problem also holds for, ready? Put on your underwater glasses. There's a lake. It's a really beautiful lake. And in this lake happens to be a Navy submarine. That's how you know it's a submarine, because it's got a periscope. Now, how does the submarine see in this lake? It sends out sonar. And the TV shows, that's always a doo, doo, right? I don't know. I don't know who came up with that sound. Someone in Hollywood, hey, let's make a sonar. So whenever you see a picture of a submarine on TV, it has that sound, right? Have you noticed that? It's like it's so deep in your consciousness now that if you were to see a submarine without that sound, you go, like, it's totally fake. But if you hear the sound, it's like, wow, that's a real submarine. Okay? Hollywood, it's awesome. But it turns out in this lake, there's these beautiful animals. Everybody's favorite animal. It's the great lake whale. Lake whale is swimming around so happy, so free. And here's what happens. This sonar comes and hits it, explodes its internal organs. Seriously. Okay? It's a problem. Now, you think I'm making this up. I'm going to show you in a moment exploded whales. The next portion of the show is graphic. Small children, please turn away. Okay, so, but I'll show you. This is actually a big problem with the Navy. I don't know if you saw in the last few years, if you've been in Seattle a while, papers, Seattle Times has run all these articles about the Navy goes and tests over here on the Puget Sound their sonar equipment to see how they can get around. They try new sonar equipment, and there's always casualties. Whales washed up. Protesters going, geez, you're blowing up whales right out of the sound. And they are. These whales are just basically having the internal organs burst because this thing will come along and they get hit by a sonar and just, that's it. Does anybody want to cry now? No, not yet? Okay. All right. So that's the story. Sonar and radar, kind of the same ideas. You watch for the bouncing off signals. From the bouncing off signals, you can tell, hey, look, there's a big underwater rock right in front of my submarine because there's a signal bouncing off of it. So it gives you eyes, in a sense. It's a still electromagnetic spectrum. It's just that it's acoustic waves, actually, in this sense. You're just sending out sonar waves and bouncing back, and it tells you where things are. Okay? So our objective then is to do the detection of this, is to try to figure out methods by which we can take noisy data in our detectors, and I know what I'm looking for, to extract that out and have something meaningful to say from that. So you came in late, and you're kind of going like, it's at cartoon time? And it totally is. We've been making up a little play story about campers and lake whales. So anyway, it's a great plot. Okay. Everybody good with that? That's what our objective is? All right, so now let's go do some programming and talk about what we want to do with trying to understand this problem mathematically. All right, so let me turn this on. Okay, good. Hey, Will, you crying downstairs yet?
What's that?
Are you crying yet about the lake whales?
I'm sorry, I'm totally...
Dude, you missed my best lecture the whole year.
I just heard Erica, and that was it.
Yeah, she's camping on my lake.
Okay.
Yeah, so I think it's both Maria and Erica are camping on the lake, and here's the story. The lake whale gets blown up. It washes on shore right in front of their campsite, and they have a big sushi party. They invite the whole atmospheric science department over, and, you know, They just have a little sushi party, and it's super awesome because, you know, whale sushi is really expensive. That's how it would go down. That's the good story right there. See, that's the positive end of the story. Okay. Yeah. All right, so let's start off with some basic programming ideas. We're going to construct, first of all, an ideal signal. And so what I want to do is start building things, let's say, and you're going to see how this builds up. It's actually very simple in some ways. This is our total time slot. Oops, let's put that in comments. So what I'm going to do is measure a signal for an interval of time. I'm going to just take in from my radar or my sonar detector, measure the incoming signal stream, the electromagnetic spectrum, for a certain amount of time. And so this time will be determined by this L parameter. Then I'm going to decompose that signal into a number of Fourier modes. Okay? So my total time is going to go from, it's going to be a linear space that goes from negative L to L in n plus 1 points. And t is actually just the first 1 through n points. Remember, periodic boundary conditions. So what I do is I'm going to work on the interval from negative 30 to 30. So my total time domain is 60. And we're not putting in units in this yet, right? Could be 60 seconds I sample time, or it could be 60 microseconds, whatever I want to do. There's some normalization or some parameters you put in. They'd be very different for sonar versus radar. Even in radar, sometimes they send microwaves, sometimes they're sending radio waves. These are very, quite a bit different in terms of their wavelengths, for instance. And so I do this, and then I'm just taking the first 1 through n. The last point is the same as the first, so that is my time domain. And what I have is the idea is, let's see if I have a signal in that time domain. Now, what I'm going to do today is do the following. I'm going to say, look, let's go ahead and say that we have the following signal. Just a bump. Okay? So what I can do is plot this bump, t versus u. And let's say that this is the ideal. So for instance, that would be my target detection. If I have this here, there's a big spike of electromagnetic energy that came back to my detector. And I say, look at that. There's something there. Okay? If there's nothing there, nothing would have been reflected. But I sent out a pulse of light. It came back, and I read it in a time frame, and boom, I get a big reflection back. Okay? So that's like, say, the idealized version. So today we're going to work with idealized things. Okay? We're going with the concepts as the main primary objective of trying to understand this. Okay? So there's my signal. And I would say, clearly, there's something there. And here it is. And I would typically what you do in a detector is you'd set some kind of decision threshold. Let's say if I'm at 0.5, here's my decision threshold. If I get a spike of energy above 0.5, I have a target. Below 0.5, who knows? Probably not, right? You have to decide. Your electronics has to decide, do I see something or not? Okay? It's a subjective issue, but you get to set where the subjective level is. Okay? And that becomes how you measure if things are there or not. So here's the ideal case. So now what we want to do with this is say, well, that's not really what you get in your detector. We have cell phones, people talking on cell phones, calling up their friends to come to the whale sushi party. Just completely clouds everything up. We have 3G networks going on, all kinds of stuff. All right? So what we want to do here is start thinking about what this is going to look like, first of all, in the Fourier domain. And then I have to add noise to it. Okay, so first, before we start getting that far along, what I want to talk about is the fact that, let's put in our wave numbers. These are going to be our frequency components because we're going to need them. 2 times pi divided by 2 times L times. So you're going to build this over and over and over again. So you should basically have it memorized. Okay. These are our frequency components. First, this piece here rescales, because I'm going to use FFTs, FFT thinks you're on a 2-pi periodic domain. Okay? So this is all about just rescaling your domain, which is size 2L, from negative 30 to 30, down to 2 pi. That's it. That's all that does. We're now on a 2-pi periodic domain, and the wave numbers are given by here. Cosine 0, x, or cosine 0t, cosine 1t, cosine 2t, cosine 3t. These are all the Fourier components. Okay? That's what these represent. The integers of things that fit on a 2-pi periodic box. Okay. So these are our wave numbers. We have our function. Now, let's go take a look at this in the Fourier domain. So it's very easy to get into the Fourier domain. We'll put plotting here later. Fourier domain, ut equals FFT, u. There you go. You're in the Fourier domain. Now keep in mind, when you move to the Fourier domain, there's the shifting and the multiplication by -1 for every component. Typically, typically what people look at when you look in the Fourier domain is what's called the power spectra. In other words, the absolute value of the Fourier components. Okay? So that's what we're going to plot. We're going to take the absolute value of the Fourier components, plot those, but we have to make sure to unshift everything. Okay? So first of all, let's start off with that idea. Let's just, hey, let's go ahead and plot the Fourier domain. I can plot FFT shift of k. Remember, k is shifted, so you have to plot it to make it look nice. You have to shift it versus the FFT shift of the absolute value of ut. Okay, so this is the Fourier transform of that signal. And here's what it looks like in wave number space. These are its frequency components, the strength of the frequency components. So if you start off with a hyperbolic secant, this is what it looks like. I'm going to do one other thing here, which is going to help us out down the road. I'm going to normalize this absolute value of that divided by the max of the app. So I'm going to normalize it to height 1. So for right now, so when I FFT'd it, had a height 30, I'm just going to normalize it to height 1, and you'll see why a little bit later. Okay? Yeah, Rich?
Value of the max? Because could you have negative, your negative being the biggest component?
Yes. So I'm going to plot everything on a positive scale. So even the negative components that are large will then be, if you take the absolute value right, I'll put those to be the height cutoff of 1. So whoever's the tallest, absolute value-wise, that's going to be height 1, wherever the frequency component is. Okay. Now, here's what I'm going to do. I'm going to add white noise to this system. Okay? What is white noise? Well, white light is typically thought of as a combination of all colors, right? Colors are just different frequencies. So the idea behind white noise is to say, oh, if I want to add white noise to a signal, as I put it in the Fourier domain, and to every single Fourier coefficient, I add noise. Right? Because every single one of these k values here is a different color, as it were. So what I do is I go through, I add to every single Fourier component some random variable. In particular, what I'm going to add to this is the normally rand n, which is the normally distributed with mean 0, variance 1. And I'm going to add a certain amount of that to every Fourier coefficient that's here. Okay? That's how I add white noise to the system. So that's a good thing to know how to do, right? If you're going to do some simulations and you want to add white noise, well, here's how you do it. You say, okay, I've got this in the Fourier domain. Now let's call it UTN, which is the transform with noise. Okay? So I think most of the variable names will mostly make sense. And what I do is I take this UT field and I add some noise strength to it, rand n, a normally distributed variable, 1 by n, plus rand plus I times rand n, 1 by n. And we have to make some noise strength up. Let's say noise equals 1 for right now. We can play around with that. Okay, so what does this do? Rand n gives you a random a vector of random numbers, which is 1 row, n columns. It's 1 by n vector. and each component of that vector is a randomly distributed normal variable, mean 0, variance 1, and I add a real and imaginary part. Remember, this is a complex field. If I just add real, I'm doing something very specific about the noise. This is a complex field, so I have to also randomize the phase, as it were. Okay, so that's what that does. Having a real and imaginary part is critical. Otherwise, you get either symmetric noise, even, or if you put in imaginary noise, then you get odd noise. Okay, so this is bad. You're setting up a bad noise generator in that sense. So you want the field to be like this. That is our noisy signal. Let's plot it. Here it is. Oh, there you go. I add some noise. You can still clearly see nice big spike. Everybody can see that big spike? Sweet. Let's look at the time domain. So let's do the following. Subplot 2, 1, 1. What I'm going to do now is bring this back into the time domain. The noisy U, UN, is equal to IFFT, FUTN. Okay? So now I'm going to get back my noisy signal, and so actually I'm going to plot that in the second piece, and subplot 2, 1, 1 is going to be plot of T versus UN. Okay, so let's plot this and this. Okay. Time domain, frequency domain, and I've added noise. At this point, you have no detection issues. I've added noise, but you can still clearly see there is the fighter jet airplane sitting right there. Plain view. Now this fighter jet decides to go and not just paint the thing black, trick it out that way, but put absorbing layers and start saying, hey, how can I make my signal coming back go down? Effectively, what this is really saying is to say, well, my signal to noise ratio changed. My signal went down. My noise level looks a lot bigger than before. So let's start increasing the noise. Okay? And this is more of the realistic. This is like a jet airliner. There it is. Okay. Now let's bring this noise level up. Let's go to 5. Okay, kind of getting noisy. You can still kind of see, though, pretty clear spike here, kind of a spike there. We know it's there, so it's partly if we could study psychology right now, which is if you're expecting something, is it going to be there? And so you're already thinking it's there, right? So you can kind of see that. Let's increase the noise strength a little more. Now, I ask the following question. You going to launch a missile at that? That's really what you're asking if you're doing radar detection. Is there a giant wall in front of me if I'm a submarine? Yes or no? It's a simple question, right? That's what you got. Low signal to noise ratio. And as far as you can tell, here's all your frequency components you measured in the time slot. Here's what it looks like in the time domain, and you go like, I don't know. Is there a bump there? It looks just as big as that one. There's some little spike. Are those things or not? Right? So that's the signal detection problem. You have a bunch of noise, and when you just look at your signal coming in, that's what you get, generically. And your job is to now think about how to clean that up, how to make it relevant, and how to actually make decisions based upon it. Now, there's 2 ways to go about this. Today, we're going to talk about one way, and on Friday, we're going to talk about another way. Here's the fact of the matter. When I look at this data, I could say, well, look, this is just one slice of time. I'm going to take another slice of time, and another slice of time, and another slice of time, and what I really want to do with all these collections of slices of time is what? Well, if this is really noise that's in there, somehow from one time slice to the next, especially if it's white noise, they're not going to be correlated, right? So I could ask the following question. What if I have a bunch of slices of time, and I ask the following thing? I use a covariance matrix. I just calculate how's this slice of time related to a second slice of time, related to a third, related to a fourth. In general, the noises should not be related, and so they're going to have a very low covariance. But if there's a signal that really sits in there from one time slice to the next, it's going to have a covariance that is higher than above a certain level. Okay. All right. Okay. See, this is what happens when you don't run enough battery, or when you run enough battery. Okay. So that is the idea. So one way is to do that. So that's what we're going to do Friday. Is we're going to start looking at, hey, look, I got all these time slices. Let's use our statistics thinking about this and start saying, hey, look, if this stuff is there and there really is a signature there, this plane is moving, right? And it's going to keep producing a signature. I want to just say, okay, so that means slices of time should be correlated. We'll do that Friday. Another thing is, when I look at this, when I looked at the data, here, where's the figure? Did it go away? Okay, I just run it again. Boom. I asked the following question. I don't care about any of these frequencies. The only thing I care about is stuff around here. I'm looking for a very specific frequency. I sent out omega naught. What am I looking for? Omega naught. So yes, I read off the whole spectrum, but I don't really care about the whole spectrum. I care about my spectrum, omega naught. Okay? So what I can do is apply what are called filtering techniques. I can just filter it around here. So let's build a filter. And let's put a filter right here. And what this filter is going to do is going to basically chop off everything else. Okay? Simplest filter, Gaussian filter. So let's build this thing, put it on this graph, and then see what we can do with this. Okay, everybody understand the problem? Kind of? Yeah? What we're going to do now? So digital signal processing, there's a lot of filters. There's whole handbooks about filter design. Okay? You can get pretty serious about filters if you want in your life. We're going to get very not serious. We're going to just do a basic filter, and then and we'll build from there. So here's the idea of the filter. The filter is going to say, I know where my signal is, and so I'm going to build a filter around that signal. All right. Let me find where I am in my notes. Oops. Okay. All right. So here's my filter. Filter. Like the rock band. We won't play a soundtrack today, but that would be kind of cool. Like, do you guys watch the videos online? You know how there's that little music that gets played before you watch the movie? We could put filter on instead. Will, can you hook us up? All right. Well, just for this lecture, because we're talking about filtering, we can put filter. That'd be awesome. All right. So here's what we're going to do with this filter. The filter is just going to be a Gaussian. A Gaussian in K-space. So let's plot this thing first. Let's plot it. By the way, the dot, dot, dot continues on the next line. So let's plot FFT shift of K versus the FFT shift of this filter. Okay? So here we go. Okay, see the filter there in green? So let's actually make it maybe magenta and line width 2 so you can see a little bit better. Okay, everybody see the filter? I haven't done anything with it yet. But this filter here, there's what it looks like. I'm going to play with it a little bit. Now, I put a width of 0.2. Now, partly because I know where this lecture is going, because I kind of worked it out ahead of time. But here's the deal. What you can do with filters? Well, you can change their width. You can change their shape. I could have done, instead of a Gaussian, I could have just done a filter that's a step function. Okay? All kinds of filter designs. There are Butterworth filters, Gaussian filters, Bessel filters. How many do you want? All of them have different properties. Some of them stop ringing. Some of them kill off ringing effects. So for instance, if you put in a square filter, this is Fourier domain after all, right? Discontinuities and discontinuities in the Fourier domain create oscillations in the time domain. So you get that in your signal. Maybe you don't want that. Maybe that's the worst thing in the world is to get those little oscillations. So So you build their filter to try to minimize it, right? That's what people do in electrical engineering. That's their objective in life. Okay? Your objective's bigger. You've got bigger plans. All right. But there's a filter. Now I'm going to apply this filter to this noise. See what I get out. So all I'm going to do is multiply that magenta thing by the blue. So this is pretty much 0 out here. 0 times all this is 0, pretty much. All right, not 0. Nearly 0 times something is nearly 0. So the only thing that's going to survive is stuff in here. Okay? Because I know I'm looking around this spot. Okay. So let's do that, and let's make another plot. Let's make this now 3 by 1s. And then subplot 3 by 1 by 3. And in this one, I'm going to plot, well, first of all, let's take our noisy, let's call this, what do you think I'm going to call it? Actually, let's stay consistent here. My transform domain with noise filtered, UTNF. Okay? And what that is UTN times that filter. I just filtered it. You're done. So I can just say plot FFT shift, okay, versus, let me copy and paste this line because that seems to be the easiest thing to do. And not UTN, not UTN, but UTNF, UTNF. And we plot this, and hopefully if we did it right, which, oh, did it complain? Oh, something I did wrong. I'm missing a parentheses. Oh, one more. There. Yeah, we put something like that. Okay. All right. All right, see how we're progressing along. See how much stuff we're doing? You take your input, your time domain picture, before you transform it, mess. Now I get something here. By the way, this could be all fake, right? You're just saying, I'm going to look there. I got all this energy there. But I got a bunch of energy over here, too. The real question is there really something buried in there or not? Right? You're really looking for, I've covered everything up with white noise, and asking if there's something there. Okay? So now I'll filter to have this. And now let's inverse Fourier transform that. Okay? And we're going to inverse Fourier transform that, compare that inverse Fourier transform versus the ideal signal. Okay? Should I do it all in one plot? 4? Yeah? 4? We can keep going. We can do 50 plots by one column. It's be awesome. Okay? All right? So we'll do 4 for now, and we'll start building. All right. Oops. Yeah, I'm pretty sure I didn't mean to do that. Okay, I don't know what happened there. All right, so let's bring this back out. All right, so here's what I'm going to do. We're going to make it 4 by 1 by 2. So what am I going to do now? Well, in this last subplot, by 1 by 4, what are we going to plot? So now what I'm going to do is take the, let's call it UNF, the noised, so not in the transform domain, but U in the regular domain with noise but filtered, UNF, okay, is equal to the IFFT of UTNF. Sounds like a chant. UTN, no, it's like there's no United States. Yeah, we need an S in there to have something to chant about. Okay. UTNF, inverse Fourier transform. Oh, not IF52. Matt, dude, you're supposed to bust me on that. You say, dude, what's going on with that too? Something. All right, so now we plot T versus UNF. And we're also going to plot, then we're going to plot that in black. And then on red, we're going to plot the ideal signal, which is just U. Plot that in red. Okay, so really the idea is this is the final piece here. We did it right. And look at that. So let's plot the absolute value. So that we don't get all those negative numbers. Look at that. Isn't that nice? Okay. So here's what we did. Started off with a noisy signal, which in one way you can't say, well, I can't tell what's going on there. But I actually know what I'm looking for. So I'll filter around that. So here's the Fourier domain, but I know my signal coming back should be omega naught. I'll filter around there. When I filter, I get this. Now, at that point, you still don't know if there's anything there, right? Which is, you could say, well, I'm filtering here, but, I mean, I would get this same shaped function if I filtered over here. We're going to do that in a moment, by the way. Just to close the deal. And so there are no more doubters and skeptics in the audience. It will no longer fall under the realm of witchcraftery, as I've been accused of selling in this class. It will now fall on the level of science or something. All right, so we're going to shift it around, but we did it here, and we pulled this out. What is the red? The ideal signal. What is the black? It is our signal that we got out from post-processing. Okay, now let me draw a decision line here, and the decision line might be something like this. One thing, I'm going to say, let's plot a line that is between negative 30 to 30 in x, between and 0.5 to 0.5 in y, and plot that with a black dotted line. So why do I draw this line? Because when I draw this line, I want you to understand that the detector on some level, you're not seeing this as the human operator, right? What you're seeing is your detector is going to be set to a threshold level saying, above this level, okay, do you remember the sonar screens that you always see in the movie? The little hand that goes around? Boop, boop. It's like that. So there's a decision level that's set that put a green dot up on the screen, okay, and tell the dude that there's something there, bogeys or whatever. Okay, that's what this is doing. So you have to set a decision level. There's a decision level, and you'd say there's something there. Now what you'd like to see is something there also, by the way, the next time around. I took one slice of data, take another slice of data, take another slice of data, and I'm hoping, so Friday we'll talk about that, but the hope is that that persists. Remember, you're making a pretty big decision about what to do with this, right? Potentially. Not always. Maybe just trying to clean it up. But you potentially could be launching missiles at this thing. All right? So you want to be sure. All right? All right. So far it looks good. But one person once asked, had the gall to distrust my lecture and said, well, wouldn't you get the same thing if I just moved it over? And I scoffed in disgust and stormed out. No, I actually just said, okay, well, let's move the filter. Let me go filter over here. Where do you want to filter? Does anybody want to volunteer a filter spot? Yeah, Jay.
Filter at E squared.
At E squared?
Yeah.
Dude. Can you give me a number like 5, 10, something?
I'd have to make it easy on you.
Well, I'm going to make it easy on myself. Let's filter like over here, like at around 15. It's just nice, clean, round numbers. I mean, I could put E squared easily into the computer, but that's just more typing. All right, ready? Now we come over here and say, okay, let's flip our filter around. Let's go filter centered around 15, around that wave number. Same thing. You know, this looks pretty close to what we had over here. So this is very deceptive, right? This is the part of the detection issue you have to understand. When I see noise, not all noise are alike. The noise that was here was sort of a coherent set of noise, which is all this noise was essentially, when I see a big spike of information, it was coherent, all in phase. It still looks like a little bump just like this, but when I look at this noise over here, the reason I know it's actually pretty much white noise is that everything's out of phase. So when I plot it just on a spectral plot like this, you can't really tell much. But then when I inverse Fourier transform it, the fact that they're all out of phase, here's my ideal signal. What do you see here? The black is what I get back. There's no signal there. Okay? You're not going to launch anything because what your detector did, sliding this thing around, you found, oh, look at that. There was something here, clearly not something there. Super sweet. You guys ready to be radar detectors in your life? All right. Okay. So here's the deal. Let's play just a little bit more since we've got a few more minutes. Let's talk about changing the filter width and see what kind of impact it has on this thing. Okay? We're not going to change the filter shape, but we'll have something like this to look at later. So here's the deal. Let's go ahead and come back. Let's bring this back. I hope you weren't too disappointed, Jake, with 15 instead of e squared, but that's pretty close. It's not too far away. I mean, you know, same order of magnitude. It's all relative. So let's come back here. Let's look at the ideal situation. There it is. There's the ideal thing, pulling out the signal. By the way, let me just make a following point before we change filter strength and design. There's always a chance that the white noise that got added was just right to make whatever, a type 1 or type 2 error, which is you drop this peak below this line. In other words, there's something there, and you said there wasn't. There's also the potential that you added, there was nothing there, and you added noise in just the right way that it just happened to produce a little spike there above the detection threshold. And so all of a sudden it says there's something there when there's nothing there. Okay? You always have the potential. The hope is then to use different time frames and their correlations to say, look, if there's a statistical spike, it doesn't matter. It's going to be washed out over a bunch of time slices, and something that's really there is going to actually persist over time, and I can make an accurate detection. Okay, so let's look at that, and then let's now like change the filter width. Like, for instance, I can change it to 0.5. Now my filter is much narrower. And what did it do? Well, now I'm cutting off a lot more frequency components, getting a much narrower thing here, and you can see this drops the ability to detect quite a bit, actually. So you have to set your decision threshold differently. If you make, and this makes sense, if you can make a really, really narrow filter, you're cutting off a lot of the signal you're getting back, actually. Okay? So you don't want to do too much like that. Now let's make a very broad filter. Let's bring this to like 0.05. Now 0.05 is much broader. You get a lot of stuff, but now you're getting actually a lot of white noise in there. Now notice what happens here. You still get a good spike here, but look how dangerously close to these threshold lines you're getting some other spots that are completely, this is an artifact of white noise. So if you make your filter too wide, you can also generate things that are, you know, you're not suppressing the white noise enough. Okay? So that's the idea. And different filter designs, see, notice also, by the way, you see there's a characteristic frequencies in here, right? This is also called, in the literature, right? It's a low-pass filter, right? So you kill off all the high frequencies, and you let the low band go through, which is, this is wave number 0, and around this wave band. So you let everything go through, everything else gets killed off. But you can see the kind of frequencies you get here are pretty characteristic. There's these oscillations. You can use filter design to try to kill those off, too. If you know they exist, target them. Kill them. You know they're an artifact of the whole signal processing issue. Okay. Have a great Wednesday. I'll see you Friday for more fun with radars. And if you want, by the way, I was going to do this in just the last minute here. And I just have to show you this because I want to just show you this. We just did a Google. Oh, I'm not online. Sorry. Here's what you're going to do. As soon as you get back to your office, you're on Google, checking your email. You're going to go over to the Google search bar, and you're going to type radar whales. Search. And you're going to look at some exploding whales. Okay? So it's super sweet. I mean, it's not, but if you're a small child, don't do it. All right.